In the first video, I presented the slogan that monoids axiomatize algebraic structure. In the second video, we looked at one particular example of algebraic structure, namely monoids. And in this video, we are going to present monoids from the point of view of monads. And we will do this both in the mathematical language and in the programming language, Haskell. So let us start by looking at the Haskell program on the left. And let's translate this Haskell program into mathematical notation. So I'll make a table here. And let's say I put the Haskell on the left and the math on the right. And so basically what we're going to do is to map the notation on the left to the notation we've seen in the previous video. So what is called the little a here was our alphabet. So we wrote this as sigma. And then what we see as list A on the left, we wrote as sigma Kleene star on the right. So list A is really the free monoid over sigma in mathematical language. What else do we have? So we have, or we see on the left in line number 3, we see nil. And this is the empty list. And depending on whether really I talk about the free monoid, I want to write the empty list as these with these square brackets. In the kind of generic monoid notation, this was the neutral element, and we called it E. Then what else do we have? So we can use this notation on the left to write, to make larger lists from smaller ones. So this on the left in Haskell would be I would just write this like this in mathematical notation. Or maybe, let's just make one more example. If I make my list a bit longer. So the cons is for constructing lists. Right, so then in the mathematical notation, that would be just 1, 2. Actually, if you use Haskell predefined lists instead of implementing your own lists, then Haskell would know the mathematical notation and everything would look much nicer. But the advantage of doing it ourselves is that we are in full control and can understand everything from first principles. Okay, so then next come the functions here. So I wrote this mult for multiplication, and this is what we just wrote as the dot before. And for lists, it's just concatenation. Then if you use predefined lists, it's just called map, but here we call it map list to avoid naming conflicts. And the map list of f, so map list takes a function, and we'll explore, we actually use the programming language itself to explore what this function really is doing. I just want to introduce here my mathematical notation for it. And then what do we have? The eta is a mathematical notation, the eta, and the mu I write as the Greek letter mu. And then for the lift, maybe there are different notations around, but I like to write it with a sharp symbol here. Okay, so next we want to understand what these operations are. So monoid operations, now we have map list, eta, mu, and lift. And we'll also have some equations satisfied by these operations. And we want to use the programming language to kind of discover what these operations are doing and maybe also what the equations are. So the advantage of doing this in Haskell is really that Okay, so what do we have to do first? We have to load this file. So let me do this first. And now I can run my functions on the left. So I mean, I can just type nil here. That's maybe not very interesting, but it gives us a nil. We can also construct larger lists. And let me do this one here. So multiplication should be concatenation of lists. And actually, if I want to give a name to the result, I can do this. So L12 is now my name for the result of concatenating two one-element lists. So let's see what happens. So I have a list with the element 1 and another list with element 2, and I concatenate them. And let's look at what this gives us. So yeah, so as expected, that is the list that contains the elements 1 and 2. Okay, so then maybe just to have some slightly bigger examples, we can now also concatenate the list we just got and see what we get here. So that should be now the list that has 1, 2, 1, 2, right? So, and we see that this is what happens. Okay, so we understand now nil and cons and mult. And let us now look at the other functions, maplist, iter, mu, and lift. So these are the ones which are really kind of characteristic of what monads are all about. And later, when we define what a monad is mathematically, we kind of will axiomatize this structure. Now we're just looking at this structure in a particular example. And so let's see what maplist is doing. So from the type in line 10, we see that maplist is taking a function as its first argument and turns this function into a function between lists. So what happens if we apply maplist to the function that adds 2? So let's just, I mean, in Haskell we can do nameless functions. So this is the nameless functions that just adds 2 to x, right? You would read this mathematically as lambda x dot x plus 2. And now let's apply this to the list that has 1, 2, 1, 2 as its element. So what do we expect? 1, 2, 1, 2. And now we apply this function, and this function is on elements. So we expect that the elements will be added. The 2 will be added to all of these elements, and we see that this is exactly what happens. So we get the list 3, 4, 3, 4. Okay, so that's what maplist is doing. Basically, it takes a function and applies it to all the elements of a list. What is iter doing? So let's just try something like iter of 1 gives us the list that contains 1. Okay, so here it's interesting that the a is a parameter, it's a variable. We can take the free monoid over a, but a could be itself the free monoid, right? So there's nothing against that. So we can apply iter also not only to elements which are numbers, but also to elements which are lists. So, so this is now already a bit more interesting. So this is a list of lists, right? And then let's see, we can now do lists of lists. And what happens if we plug in iter into maplist? So let's try this. So let's do a maplist, and then let's do an iter, and let's do L1212. So this was the list 1212. So what happens if we apply iter to all the elements of that list? Okay, so now we see that it gets a bit difficult to read. So, but why don't I leave you leave this as an exercise to you to translate this into the notation with square brackets. Obviously, we want to read this in the square bracket notation, in the simplified notation, without all the cons and nils around. Okay, so now we have a list of lists here, as we can see. And lists of lists are what we can, are the arguments of view, right? So we can just apply mu to all of this, right? So let's do mu, and then let's see what happens. So maybe we should take the time and try to understand the code and try to predict what the result will be. And this is what you should do when you go through this carefully yourself. Or you stop the video. But yeah, let's just see what we're getting here. And you see that this is actually the list 1212 itself. So here we discovered an equation which holds between all of these operations. So we discovered that mu map list eta of a list is the list itself. And this operation mu map list is quite important, and it has its own name. So this is here in line 22. On the left, you see that it's called lift. So if you go to the write-up of my notes, then you will find a series of exercises which you can follow. Basically, the spirit of the exercises is that you take this definition, and you can run this definition, you can run the code, and you use this to discover what are the equations that hold between these operations. Thanks for watching.